will see more advanced techniques that will be built up on what we see today. So the idea of these first courses is that we will see first what we mean by machine learning, what is the purpose of this field. And then we will really start very, very basic, because supervised machine learning is, can I maybe ask people to mute themselves, because I have some noise getting back. So maybe mute yourself if you don't have a question. If you have a question, really don't hesitate to interrupt me. But okay, no, it's fine. So we will start with the very basics of linear regression, where we will see how to fit such a thing, and then generalize to more complex things. But the foundation will be based on the linear regression. So from that, we will go on logistic regression, support vector machine, artificial neural networks, which are a very hot topic and well used on many topics. And we will also speak about model selection. So basically, on the different models we will see, and maybe if we have time, I will be able to introduce more models. We will see how we can effectively select the one that is best suited for your purpose. And I will also touch a word about feature selection, which is especially quite important in our field, because we have to keep in mind that the idea here is to apply all of this on materials. And so, of course, this has some specific constraints. Okay, so who am I? So like Ouloulou said in the introduction, I'm Pierre-Paul de Breuck. I'm from the Université Catholique de Louvain. And myself, I'm working with Gian-Marco Rignanese on combining machine learning with material science. So it's often called a subfield of materials informatics. So the idea is really for me to use databases of materials and corresponding properties to do models that can predict properties, generate new materials, that do also unsupervised learning to see some patterns, to see some classes of materials, and everything has to be done in sort that we can discover new materials based on the knowledge we have. And so maybe later in this lecture, will be maybe presenting you a bit about my work. So we have built a neural network for material property prediction, which is called ModNet, and we've also worked a lot on the issues of bias imbalance in material science and how we can include uncertainty into model predictions. Okay, so that's a bit about me. So about the course that I will be given. So the idea is that we do, I think, 3 times 1.5 hours per week. I will also, so somebody say no voice in the chat. Do you hear me?
Yes.
Okay. Okay, thank you. So it seems fine then. Okay. So I will so my lectures will be mainly based due to time constraints to myself. I've based the course on an existing course on machine learning, which is given at my university by the professor Michel Verleijzen. So it's the course Machine Learning, Regression, and Dimensionality Reduction. And so the upcoming slides will be taken from that course. Maybe one thing I see now, do you also see this red paint from someone on the shared screen or not?
Yes, yes. We see it.
Yeah, we see it.
Okay, is this normal? So I am totally new to giving lectures on Zoom, and so I'm not used to how this works. So I don't know if it is like a collaborative sheet or something. So I don't know if the people could erase that who has done that, but
No,
it's fine.
I think you can use Laba.
Sorry? Okay. Anyway, I think it's fine. And so if you have questions, curiosities, here you have some very good reference books I've listed on machine learning, but it's not limited to these ones. I would also suggest to go a lot on the internet, go on Google, Wikipedia, and a lot of good websites, even YouTube and or online courses have a lot of information on machine learning. Machine learning is a topic you can find almost everywhere on the net. And so I think by reading, you can very quickly understand the basics and really do some good modeling. Okay, so I've spoken about the structure. So I will try to introduce the theoretical concepts. So it's important to have at least a bit of understanding of what happens at the theory, and then at the second level, I will also like to have notebooks where we will really try to implement ourselves the models and where we will fit on existing data. And so please ask questions when I speak, interrupt me. We can discuss. So I mean, the purpose really here is to have something that is interactive, so that we can really learn together and that there is no misunderstanding from your side. Okay. Okay, so let's start with the introduction. So what do we really want to do with machine learning? So there's one definition that I quite like from a professor that is very excellent at teaching machine learning, that says that a computer program is set to learn from experience E with respect to some class T and a performance measure P if its performance at task T, as measured by some criteria P, improves with experience E. So what does that mean? It means that basically you give data and the machine learns. And when you give more data, the machine will get better. So it will be smarter in some sense. And this means that when we measure some performance P, so this could be let's say the average error we have on prediction. If it decreases, we say that it's learning, and so it improves with the experience, and experience is the data. Okay, so really the key thing here is machine learning is based on data, and more data means more effective learning. So there are a lot of types of machine learning. It's evolving quite fast also over the years, but what I will be mainly focusing on in my part will be supervised learning. So supervised learning is the idea that we will have some machine learning model box. We will later on see what this is. And you give some information. Let's say for now, just make it simple. You have an input. For instance, a photograph of a fish. And then it says at the output what type of fish it is. It can be a sea bass. It could be a salmon. It just gives you what the fish is. So in order to be able to make something like that, you have to give to the machine a lot of examples. So you give a lot of fishes and what it is. So this is a sea bass. And then you give another picture. So you have to give examples and then you can predict. So supervised learning, the key concept is that you have input and output that are given before you start. So you have this at hand when you start.
Sorry, Pierre-Paul,
Yes.
could you stop sharing and then share again? So I will see maybe this scribble will go away.
Okay, let me do that. I will also shut off my my webcam so that there's better bandwidth.
Oh, okay, yeah.
Okay.
Yeah,
Is it better?
it's perfect.
Okay, perfect. Let me just put back the chat and the participants. Okay, perfect. So I will try to look at the chat so you can put their comments, but I think it's even better if you just start speaking, because otherwise it could happen that I don't see it. Okay. So supervised learning. I just explained this. So unsupervised learning is, again, you start with data, but the difference with the previous step is that you don't have the output. So here I give example of fishes, and I know beforehand what each fish is when I give it to the model. Here, for instance, I would have different kind, let's say, of fishes, and I only have the photo, for instance. And then the machine would see, without even telling him what it is, he will see that, okay, this is one same group of fishes. This is another group of fishes. And then here we have another group. So it would see patterns, clusters in data. So that's why it's also clustering and dimensionality reduction. But the idea is that you don't give the label of each sample. So later on, I will define the exact terms, labels, features, etc. But here the idea is just to introduce a bit the different things you can do. We also have reinforcement learning, which is the idea that computers can learn from rewards. So it plays a game, you give a reward, and then from this reward, it tends to improve and learn to get better at each game it plays, basically. So you may have heard about a lot of words like machine learning, artificial intelligence, deep learning, artificial neural networks, and how is this structured? So the idea is that artificial intelligence is like the broad term of everything that resembles to an intelligent machine. So everything that has a form of intelligence can be put inside artificial intelligence, and machine learning is something that tends to be that. So it's inside artificial intelligence. But you could also have other things, for example, let's say, I don't know, some intelligent program that is only based on if else, do this, do that. It's not really learning on data, but it can have some intelligent behavior. So it's still an intelligent machine, but it's not learning. So it's not part of machine learning. So machine learning is really based on data that makes it learns. And then inside learning, machine learning, you have deep learning, which is a special group of models based on deep neural networks that have many layers, and that can be very accurate on for instance, recognizing faces and objects in images. Okay, so this is a bit the structure of these different things. And so before we really get started in the first models, why do we really want to do all this? So with the perspective of
sorry, excuse me, can you just repeat what is the difference between each layer? I'm sorry, I didn't get it.
here?
Yes, what is the difference between each layer? what makes me think about something, it's a deep learning, what makes me think this is a machine learning, what is artificial intelligence?
So, so the first important thing is here, these are different, let's say, terminology points that inside of them have smaller parts. So let's start with the inner. So deep learning is, it's a type of algorithm that from, let's say you have an image of someone, you give it to a model that, and we will see it later, it's a neural network that has many layers, maybe with convolution, but the thing is that it is deep. So deep means that it is has many layers, so you have to go through different layers before you know, for instance, I don't know, the color of the hair or something. So it predicts something here, or let's say if it's a man or a woman. So you have two possibilities. So if you have these algorithms, this kind of structure, this is deep learning. Okay. You could also, let me think, make, and this has been done in the past, you have, again, this image, but then you have some code that looks at the, let's say, the width of the face, at the height, at different things. And so you encode this in a vector. And then you do a simple linear regression. So we will see later how this works. It's another model, and then you get man or woman. So it's not a deep model because it's not based on this convolution. It's very simple. You give some descriptors of how it works. So it's not inside this, but it's still machine learning because you will fit this model, this linear regression. We will see later again. So it's still the introduction, but then it's based on only other types of models. So this is machine learning. And let's say that all of this can be called artificial intelligence because you're making intelligent machines. But I could also make some code that say if beforehand, if the height here of my picture is bigger than something, I say I return it's a woman. So it's not, it has not been learned on something. I just give it because I think I know how it works. It's somehow intelligent, but it has not really learned on data. So it's not really part of machine learning, but it's still an intelligent thing. So is this a bit more clear or not?
Yes, yes, thank you. It's much clearer.
Okay.
So what is the difference between neural network and the deep learning?
So good question. The neural network is something that has neurons that pass through next neurons, and so you predict something. So you have input and again output. So the neural network itself is a type of model. It's a type of architecture. So it's the idea that you put neurons to make a prediction. But there is no limitation. You could just say, and let me add this a page here. You could say, let's make a neural network that has only one layer. And then I directly predict my output. So again, let's say I have this picture and I could have done the same idea of here. So I put the width of the person, the height of the person, the color of the hair. And with just one layer, I predict if it's a man or a woman. This is a neural network, but it's not really deep learning because you only have one layer. Deep learning, the idea is to combine many of these layers. You have really a lot of them. And you will see later that you can have different types of layers. Some can be convolution. But the idea is that you really have this kind of deep structure. And this is called deep learning. It's really the idea to combine efficiently many layers. Instead of here, this is still a neural network, but it's not deep learning. Okay? I don't know if the person who asked the question is still here.
Yeah, I got it. Thank you.
Okay. So back to material science. So the idea is that we have made materials over the years by a lot of different paradigms. So paradigms are, for instance, by doing experiments, I can see if my material is resistant to heat or not, because if it's smelting or something, I can just see by my eyes it's not the good material. Then we had, and there are a lot of different types of experiments we can do that can be much more complex, but it's something that is quite time consuming. The second paradigm is based on physical laws that make up a set of equations that really characterize from mechanics, thermodynamics, how my material behaves. And so I can make predictions of what could be some good candidate. Then from this, we have built up codes that use the physical law. So basically the Schrödinger equation that has then been simplified with a lot of approximations to have the density functional theory, molecular dynamics, etc., where we can really, with the computer, see how this evolves. And this has led to a lot of data. So we have, over the time, create pairs of, let's say, compounds and their properties. And now, with this knowledge, we can really begin to build these machine learning models that learn from the data creation in order to really capture the knowledge. So because you have data that has been created over time, so you have time and here the amount, you have more data, you have more information, because data really contains information, but we don't really capture the information. And so by using machine learning, we can really capture the information and learn to propose or accelerate at least material science. Okay, are there any questions about the brief introduction that will still continue here? No questions? I'll check the chat. Okay. So you see now I'm back using the slides of the source I'm giving here, which is a very good course for machine learning. Okay, so I'm back to the example I gave before about the fishes. So let's say we have this image and you want to know which type of fish it is. So for simplicity, we say there are two possibilities. There can be a salmon or it can be a sea bass. So how does it work? You get the picture, you do some pre-processing, you get some features, and then you use another layer classification that will, based on the features, say it is a salmon or a sea bass. So let's see in depth what the feature extraction can be. So these are really the fundamental elements in machine learning, because these will describe what you have as data. What is your input? Is it light? Is it dark? Is it white? What are the properties of what you see? And this is then encoded into features. So let's say for the fishes, it could be the length, the lightness, etc. And so if we plot some histogram here with the length of the fish and the number of samples in my data set I have, I see I have a lot of salmons that are quite short, a bit here. And the sea bass is a bit the opposite. It has longer length, more samples are longer and less are smaller. So I could say, I could learn that, okay, I have some threshold, and below that threshold, I have a salmon, and above, I have a sea bass. I can then do the same with the lightness. So I could look at how light the skin is. So if it's dark or light, I see that if it's quite dark, I could have a salmon, and if it's light, I could have a sea bass. Why? Because from the data, I see that most of them have a more lighter skin. But of course, this is not perfect. You see, I could have a sea bass that is here, because you see there are some sea basses too that have a quite dark skin. With my machine or with my criterion, I would say, no, it's a salmon because I'm below this threshold. But this is an error. So a single feature, just looking at one single feature is not enough. I have to combine the lightness with the length and maybe a lot more features. And that is really the power of machine learning, is to combine many, many, many different features. And by the way, features is also called often descriptor, or sometimes also fingerprint. These are things like length, lightness that describe the image. And so the power of machine learning is combine many descriptors to form something that can, through all the descriptors, predict quite accurately what you have as fish, for instance. Okay, any questions about this? So everyone gets what's the idea of the feature. So now, if you combine lightness and width, we have that it's already much, much better than before. So before we had quite an overlap that was not perfect. Here in 2D, so we have lightness at one side and width at the other side. We see that most of the salmons are at the bottom left, and the sea bass is at the right top of this two-dimensional plot. We still have errors. For instance, this is a sea bass that is in the salmon region, and the opposite too. We have here a salmon in the sea bass region. But you see that by increasing the dimension, we can create, and even with a simple model that is a straight line, we can begin to classify in two classes based just on simple descriptors from the data. Okay. Now, why do we need really machine learning? So you could say, I don't want to learn. I know that sea bass is small, is width, and let's say that you can easily make a rule that if this is the length, this is the type. Well, this is not easy to do because you have very often you have too many possibilities. Let's just take the example of an image that has 256 by 256 pixels. And for each pixel, you have an A-bit image. So A-bits means that you have 2 to the power of 8, which is 256 different gray levels. How many different images can you make? Well, a lot. And basically, you have one pixel can have 256 possibilities times the second pixel, so you have 256 to the power of the number of pixels. And here, for simplicity, I have taken an image of that size. And if you compute this, you get approximately this, and so it's huge. So you cannot make a rule that if you see this, it's that. You really have to learn to have a general rule that based on the what you have. So the thing is, and that's really important in machine learning, is that you learn on something, but when you use the model, you predict on something else that will definitely be different from your learning. And so you should be able to generalize to unseen images. So that's important, to have something that is more flexible than just a table that remembers what it is. Again, an example on features. Let's say I have a character and I have an image of the character. So these are the pixels. And I could just compute the ratio of the height to the width. The height to the width. So you see that for an A, it's quite a square, so the ratio is quite low. And here for the B, it's higher because the height is definitely higher. So again, you could make some learning rule that says, okay, if it's below that threshold, I have an A or I have a B. So that could be an example of a feature, the ratio of the height to the width. Okay, so I've now spoken about the idea to have features, really important to describe the data, and the necessity to have several features to describe what you see. But the idea is also to not have too many features. But if you begin to put very much descriptors, what will happen is that you suffer from the idea that you have a very high dimensional space. So I just introduced the issue now. Later, we will see why this is really problematic. But if you have too many features, what happens is that the machine will look at things that are not important. For instance, I don't know, you have, let's say you have something as a spot on the image, because I don't know, there was a problem with the photographer had made an issue that you had a spot, so some kind of defect on the picture. Each time it's a CBAS, it will tend to think that is a CBAS because of that, which is not a true thing. And so often noise can be introduced in data when you have too many features that will tend to do wrong prediction. So have several features, but not too much features. Okay, because classification methods are easier in small dimensional spaces. So as you will see, machine learning is really a very multidisciplinary field that is based on many fields such as statistics, mathematics, computer science. So the real difficulty will be here to a bit be at least rigorous, do a bit of mathematics to introduce the models, but also try to apply and use computer science to really make predictions. And so in a real context, it's quite complex because you have to get the data, which is not an easy task. You have to pre-process it. You have to analyze if it's correct. You have to build the right algorithm, etc., which is quite often a long task. Okay, are there any questions up to now?
Yes.
Yes.
It means that machine learning is only used for classification of material.
So it's not only used for classification. So maybe let me just skip a bit. The different types. Here. No, it's not here. Okay. So we can either have classification or regression. So these are two important words to know. Classification is the idea that the output is continuous. So let me put this like this. So output is continuous. And then for regression, no, it's the other way around, sorry. So when you do classification, you have features and you have a label that is discrete. When you do regression, for the same features, or I mean, the idea is to have an output that is continuous. So you can both do classification or regression. They are quite close because both you predict something, but in case of regression, you really predict something that is continuous, and in classification, you predict something that is discrete. So you can see here the example. Based on x1, x2, you predict some continuous map in the y space. And here you predict just C1 or C2. So it's really a color, it's discrete. Was this the question? And so I also spoke about clustering. So another thing we will see, maybe not in my course, but in the next one, is that you can find clusters inside the data with some types of models. Other questions? Okay.
Yes, sir. Yes.
Yeah, yeah.
Yes, thank you very much. Like that, we do not need to enter codes in machine learning, isn't it?
Why not what?
Not using codes, entry of codes, the programming.
Why we don't use codes?
We do not use codes.
So we do. So I don't.
In machine learning.
So you have to know that.
How can we enter the program or programming?
So based on simple models, which we will develop just after in the next chapter, you will have some set of rules, and then we will code. I mean, this will be the first homework we will do after this lecture, is that you will code yourself a linear regression, which is quite simple, but you will code how it learns by adapting the weights. So we will see what the weights are. So you adapt the weights, and by code, you learn something that you can then use to predict. So code is used, but you first have to develop a mathematical model that has to be coded.
Okay.
You see?
Okay, fine.
So I have another question here. What is pixel in machine learning? So a pixel is, let's say, the discrete building block of an image. So when you have, it's I mean, it's not a machine learning term. It's really the building block of an image. You have different squares or rectangles inside a rectangular image, and each square has a color that is defined by often an RGB, so red, green, and blue. And you have between 0 and 256, 0 and 256. So if it's 0, you don't have that color. If it's 256, you have this color a lot. And so you can define a triple for each point, and then you have an image. So you see it's huge, but the pixel is really the building block. Please talk about the regression and classification again. Thanks. Okay, I can do that. Because it's important for the rest. Let me give me an example. So I can give examples of what I do in my work. So let's suppose we have a composition. For instance, I don't know. Do you still hear me? Because I hear an echo inside my earphone. I think it's just someone with a bad connection. So let's suppose you have a composition. And I want to classify if it's either metal or non-metal. So it can be, let's say 0, it's a non-metal, and 1 means it's a metal. So if you want to do something like this, if this is your purpose, you have to make here something that is classification, so a classifier. Now, suppose you want to do something very similar, but you want to predict not metal or non-metal, but you want to predict from the composition again. You want to give the band gap in EV, so in electron volt, and so it can be 0, 0 point something. It can be any value, so it can really be anything. If this is what you want to do, then you have a regression. So 2 different types. This is called regression. Okay. I think I've answered all the questions. Okay. Okay, so let's really make the first learning algorithm, and this will be the linear regression. And you will see, even for some of you probably already know this, and it's maybe quite easy. From this, you can do a lot. We can make, in fact, what is called the perceptron from the linear regression. We can then, from the perceptron, make the neural network. And so you can really very quickly scale up from a simple linear regression to a neural network. So I have a question, sir, is coding an essential part of machine learning? Yes, because if you want to do machine learning, you will have to write, you will need to import the data, you will have to learn the data. So some code is really essential, but it's not very difficult. It's really basic things. It's not low-level code. It's high level. And you will see the first notebook I will give you today will be probably the most difficult one, because I will ask you to develop your own model that learns by yourself. So you will give how it learns so that you understand how it works. After that, it will be much easier because you will just use the libraries you have in scikit-learn and in TensorFlow, so things that are just there that you can just import and predict. So a bit of coding will be unfortunately quite necessary. Okay. So let me just introduce this. 1 second. So let's take the example of before. We have a composition. Let's say for now, just we put some elements. And we want to predict for now the band gap from this. First, this problem can be translated mathematically in something that we will call here the descriptor. So this is X. And the property is often called Y or T. So I will use Y or T in this course. I will use T today, I think. And so the idea is I want to have a function f that given X and given W, I will explain what is W, I have my target. So I have my band gap. So it's a function f that takes the input and you get the target. So I have put a hat here because it's an estimate of what it could be. So it's not the real value. And these are the weights of the model. So this is something that defines what your model is. And so when you train, you will tend to adapt the weights so that this function f tends to be the best possible. So this is the purpose of learning. You want to make this function f. And of course, for doing that, you have to learn. And learning means you give examples. And so you give a set of x and t. So here it's not the t hat, it's the real t, it's the real target. So I don't know, you have some material and the real band gap. Here is the approximation made by the model. Okay, so I will introduce a little bit of algebra and mathematical concepts here. So the idea is that we will do linear regression. So linear regression can be written as the target. So the y equals weight times x plus some w0. The feature matrix, the x can be written as a number of features. So remember that each sample is a vector. And this, just to give you an example, can be, let's say, to give back the example of the sea bass, of the fish, we have the length of the fish, and we can have the color of the fish, and up to n different features. So one big X is one example. So the weights is also a vector because for each feature you multiply this by this, etc. to have the final solution of the y. For simplicity, I will write the bias inside the weight. So I put a 1 as first feature and W0 as first weight. So therefore, I always have this constant bias term. It's just a simplicity to have the notation as a simple dot product. Okay, so we have this idea. The target is the product of the weight times x. So x is a column vector, and W transposed is now a line. And so I have the weights times the features equals my prediction TP. So I can now define this for I define the subscript here P, which is each sample I have in my data set. And Y here is each weight. So the Y are the different weights, and the P is each other fish I see. It's a new sample I show you. So P patterns, so P examples, and D parameters. The parameter is the number of weights, so the number of features for each sample. And so the idea now is I want to have the best weights such that this criterion is minimal. So here I decide to take the difference of TP minus YP, so the target minus YP. So here I think I've defined, so the one is the true label. So okay, let's say that this is the true label. So it's what I know it is. This is the prediction. And so if the difference is big, I made a wrong prediction. And so I have a big error criterion. So it's really the basic building block of building the linear model here. So you see it's the difference squared. So if you make a plot in 2 dimensions, the red line is my model and the blue is the true value. I can say, okay, I make some approximation. This is my model. And this green is each time the difference between the true and the prediction. And then I square this. So of course, this is not always the best idea. Why? Because let's say I have, let's make a very simple example. I have some points, and I have 1 point here. So when I have 1 point here, this is what we call, it's an outlier because it's quite different from the rest. But let's imagine, I mean, it's a bit an extreme, but sometimes you don't really see it, or it's a bit less extreme. When you do a linear regression with the least square criterion, you will make a line that is not like this. You will make a line that is like this, or even or a bit above. Why? Because if you have this solution, because you have here a quite big error, and you square the error. So this, let's say this is the error squared, is huge. And so it will really tend by the square, it will really attract the line to that point. So the point will really be attracted to some outliers due to the square of the error. So it's a convenient thing to do, but it's quite sensitive to outliers. So that's something you should keep in mind for this criterion. Okay. So I've explained here a bit. You can look at in depth afterwards why it's not the best idea. Okay, and so now I can also rewrite the loss. So I will go from this loss to this loss in vector form. So the idea here is quite simple. Is where is my pointer? Here. So this is the error for one point. So it's one line here. What I can do is I can introduce back X to be the set of all my data points. So I have 1 to P points. Each point here is a line. Remember, it's all the features, so the length, the depth for each sample. And so I have a square matrix where each, it's not a square, so it's a matrix with the number of lines that is the number of descriptors. So let's say I have two features, length and width, so it's only 2 lines. And then the columns is the number of points I have. So if I have 500 fishes, I have 500 columns. This is the definition I take here. Attention, because sometimes it's the opposite. And often people put as a line one sample, so one fish, and the column is the features. So it can be sometimes transposed. The target is then each time it's again, the target itself is a column vector. So when I take the transpose, I have a line vector with, let's say, the property I want to predict. It can be here the band gap in EV each time for each of my compositions. Okay, and so when I have this, the error criterion can be simply written as the transposed weight matrix times X, because if I take the weight matrix, which is like this transposed times each row, I have all the targets, and I take the difference. I take the norm squared, and I have the error for all my samples. And so now the idea is, with my sample model, I know that the model is a dot product. I want to minimize the difference. I now want to know what is the solution of this. Okay, so I want to know what are the best ways that minimize this. And so this will be the next slides, is how I find this W. But what I want you to remember from what I given now is that in machine learning model, how does it often works? The first thing is to define a model. So here we say, okay, y equals, let's say I will make it simple. We have two features, so I want to know it's alpha x1 plus beta x2 plus some bias gamma. This is my model. So I define this, it's just linear. And then 2 is I define a loss. Very important to define a loss in machine learning. And then you say, okay, I want that the difference between y and what I want to predict, I sum over all my points. I want this to be minimal. And so this together with this will define the solution for these these 3 parameters. So here I have only 3 parameters. If you have more features, you have more parameters. And typically a neural network is not that different from this. You have thousands, if not millions of these parameters. So these are the weights that you have to, again, find such that this is minimal. Any questions? Divide by the number of E. Yeah, that is a good point. You can indeed take the average. This is just that it is scaled to be the average number of points. So I can here divide by, let's say, big P, if it's the number of points, or big N. I mean, it depends on how you name it. And this is what I did here. Okay, so it's 1 divided by P because you take the average. So it's here it's the mean squared average error. So it's called MLESMD. Okay. Yeah, thank you. Something else to say?
So what is the meaning of this T you put in the roses?
Sorry, what's the meaning of the?
TI. TI.
TI. Here?
Yes.
Okay, so this is because you have a prediction by the model, which is Y. And this is the target. So what's the difference? The target is the real values, the true value. You know that the band gap is 2 EV. But the model says, oh, it's 4 EV. You have an error of 2 EV, and so it has to go back to 2 EV. So that's really the difference. One is the prediction by the model. The other is the real value. And so you want, of course, that the difference between the two is as small as possible. Okay? I don't know if it is clear. So, I mean, often you have different notations. Here I put T, Y. Sometimes people use the hat to show it's a prediction, and then you have Y hat minus Y as error squared, 1 over P sum, because you have the prediction minus the true, but it's always the difference between prediction. Well, I mean, it's a function of the true value and the predicted value. Okay, so now, like I said, the idea is we want to find the weights of this thing. So 2 possibilities. First, that you mathematically compute the solution. So for that, we have the error criterion. We compute the gradient of the error. So you can compute what is the gradient with respect to the weights. And then you say, okay, I want this to be 0, because of course, when you are at the optimum, the gradient is 0. And so you do the derivative. Maybe for sake of simplicity, because we are a bit late on schedule, I will not do in depth this, but really please ask me if this is not clear. I can do this step by step. And so one important thing to know is that the derivative of the error with respect to the weight is this. So this is for weight G. You have here this, so it's the weight transport times X minus T transport times feature X of J.
What is P?
Sorry?
What is P? P.
P is a number of points you have in the data set.
Okay.
Number of patterns, it's P of patterns. And so I skip a bit the math to save time and not to lose you. The derivative can be written as this. And then when you equal to 0, you have the solution as follows. So you have an exact solution. I mean, it's exact in the sense that it is mathematically the optimum of the loss criterion, which is equal to x times x transposed inversed dot x dot t. So my question now is, why is W not just something as, let's say, if I take the, so we have said that y equals, we have defined it as v, okay, weight transpose to have a line times x as a column. If I could just say, okay, Vt equals my target times x invert. So I can just invert x, and then you agree that if I plug this in this, I just have this and this cancels out, and I have my target. Why does this not work? Anyone an idea? So the solution, the answer is that basically this, the inverse of x, it's just not possible to compute this because it's not a square matrix. You have to it has to be squared to compute the inverse. Here it's typically the number of points, the number of patterns is not equal to the number of features. So you cannot just inverse this. So you have to do this thing, which is called the pseudo inverse. Okay. So this solution is something that will work. So you have, let's say you have the data X, okay, you just compute this, I have my weights and I have my model. But it requires to compute the pseudo inverse, so the inverse of X times X transposed. And often because you have a lot of points, a lot of features, this is a huge matrix that is often not well configured, and you will have issues by inversing it. Even more, suppose that you have some active flow of data coming in. So you have a model today, and then this afternoon someone comes, okay, I have made new experiments, I have new points, I want to improve the model. Here are the points. What do? Well, you have to again compute everything. You have to again take your big X matrix. So remember the columns are different points. So if this morning I had this, then someone comes this afternoon with new points, I have to add this to the matrix and then recompute this thing, which is time quite consuming. And so it's not the best idea to always work with this solution. So there is a second solution, or let's say a second way of finding the optimum for the weights. It's with gradient descent. So gradient descent is an important concept to find the minimum of some function. And here the function we want to minimize is the loss function with respect to the weights. So a quick reminder, if I have some function f of x and function of x, I have a question coming in. How do you carry some of us that joined very late along? Okay. I mean, I think it's recorded. So anyone who's coming in late, you can really listen again to the course. And so I also skipped one thing. Sir, I suppose the bolded letters are matrices. So yes, this is a good point. So it's not always a matrix. It's sometimes a vector too. That when it's an uppercase, it will be a matrix. So here This is a matrix, it's uppercase. This is a vector, this is a vector. In this case, okay? So again, about gradient descent. So the idea is that I have my function, and if I compute the gradient will give the direction to the minimum. And so if I am here, x, y of t, so y is just one time step. I compute my gradient. I take the negative of the gradient, which is pointing in that direction. I have some displacement alpha times this direction, and I go closer and closer to the minimum. So gradient descent is the idea of always go to the next point, recompute the gradient, go to the next point, recompute the gradient, next point, gradient, next point, and so you finish here. This alpha is quite important because this is giving the length of the steps. So if alpha is small, it can go very, very slow, a lot of iterations because you don't advance. And by the way, the danger is also if you have some local minima, which is often the case in more complex models, that you do gradient descent to find the lowest point of your loss with a small alpha, and then you're stuck here because you don't go away. You don't go away. If you have a little bigger alpha, you can do this, then you go here, and then this point will go here, and then so basically you jump over this local minimum because you're not falling perfectly inside the local minima. If it's too big, it's not working too, because if it's too big, what happens is that you will compute the gradient, for instance, here. You go up, let's say there, because you go that direction, but too far, and then you recompute the gradient, you go again there, and so you basically are skipping left, right, around the minimum. So this should be well tuned, and you will see there are a lot of parameters to tune in machine learning, and this is often called the learning rate. Okay. So this is an example. I will skip this. So back to our linear regression. We want to minimize E in function of W. And so my gradient descent is, I have some weights at time step t plus 1 equals what I had before minus alpha the gradient. And so the gradient here was alpha, so the learning rate times x times t minus x transpose w. So this was what we found here as derivative of my loss. So, okay, and this equation will iteratively update my weights, and so I will tend to some solution for my weights. So you need to have some iterations. You don't need to make the matrix inversion, so that's a good point. You just have to compute the loss with x, but you still need all the input-output pairs here because you want to compute this on all the points. So this is a vector, this is a matrix, and so you want to have all the points inside to compute this loss times x to have your gradient. Now, one thing you could do is, okay, let's say I don't compute my gradient on all my points, but I compute this only on some points. So instead of having everything, I have only a sub sample, or even further, you could compute it on one single point. So you can have my error on one sample. Okay, no, so it's decomposed. So, okay, let's say we just take this part, so one sample. And instead of minimizing the whole energy curve, I can equally minimize the error I make on each point sequentially, and I will also tend to some minimum. So, and this is the idea of stochastic gradient descent, is that instead of computing the gradient, this is really the basic idea, instead of computing the gradient on all my points, I compute this on a sample of points. And I update my gradient only on that subsampled set. So this subsampled set is often called the batch of points I use. I don't think it's written in here. No, so here they speak about each error of k individually. But the idea is that you could compute the gradient let's say we have some sampled set. So this would be the gradient of the sampled set. So it's not all my points, but just some points. Okay. And I do my learning rate times this gradient, and this is what I will use at each time step t. So this is the advantage, that you don't need to have all your data. You could basically have an optimum of your linear model with existing data. Someone comes with new data, you can simply only compute the gradient on this new set of data, and again minimize your solution to a new optimum that is taking into account this gradient. So the idea is that you can really have something that is stochastic with respect to the points you include to compute your gradient. And the idea is that you, by average, you take a bit everything into account, and so you tend to this global minima for the weights. So here I compare a bit the pseudo inverse versus the gradient descent and the stochastic gradient descent. So basically, for the stochastic, you don't need all the points. For the other two, yes, you need. Here it's only one big computation. Here it's a lot of different small steps. Matrix inversion, yes and no, of course. And then if it's sensitive to order of patterns, here it's not sensitive, here it's not sensitive, here it might be. If you start to compute the gradient on one batch and then another batch, you could tend to another solution that the other way, because logically you have another gradient depending on the batch you take, and so you can tend to different solutions. Okay. Any questions? If not, I'll maybe make a small break of 3-4 minutes to do the last part.
I have a question. How do you choose the point to minimize the error for? If we don't want to do it for all,
okay,
how do we choose which one we want to minimize, or it's arbitrary?
So often it's arbitrary. So to give you the, and it may be a good point to introduce a different terminology. Let's say I will make it visual to make it really clear. You have all the data. Let's say it's shuffled, so you're sure it's random. Often we will divide in batches. So you can choose the batch size. So let's say you have a batch size of 64. You take 64 points, 64 points, 64 points. So this is called the batch. Then you take these points, the first batch, you compute E. From this, you compute, oh, my pencil is just very slow. You compute the derivative of E with respect to the weights. And then you say, okay, I update my weights such that at the next time step, my weights are these I have now minus my learning rate times the derivative I just computed. And you repeat this for each single batch. So you repeat. So it's totally random, the order, because you have shuffled the data. And once you have done all of this one time, you say that you have gone through one epoch. This is one epoch, okay? And then you can repeat again. So you have epochs, and inside the epochs you have the batches. And what you see is that when you proceed over the epochs, so what you should remember is that one epoch means that all the data has passed through the gradient, and you have seen all the data once, and then you can repeat multiple times. And of course, when you do this, what you see is that your loss or your error, so how you define what you want to minimize, is of course decreasing in function of the epochs. So it's a random process, which is best. Of course, you have to choose what is the batch size. You could go up to choosing 1 as batch size, so that you do 1 point by 1 point. You also have to choose the number of epochs you do, because often it can happen, but this will be seen later, that you tend to overfit, and so the error is increasing again, and things like that. But I think this concept is important to understand, that you have data, you compute for each batch the error, the gradient, you update the weights, you repeat. 1 epoch is done, and you start over again to the second epoch. Okay? And so this is model independent. You just compute the weights with respect to the error that is given by the model, but I mean, the workflow here is really model independent. It can be a neural network, it can be a linear model, it can be simple perceptron, it can be anything.
Okay, thank you. So we have two random selections, number of batch and the number of epoch. They are random. I could do it hundreds of times, or maybe 10 times or 1,000 times.
Typically, this is something that you have to follow the learning curve. This is called the learning curve. You have to see, okay, decrease, I continue. And at one point you see, okay, no, it's a bit stationary, so I can stop.
Okay, thank you.
This we will see in the practical sessions, how to see this. I'm not clear in the concept of linear regression. Could you explain with simple practical example? So linear regression is the idea that you have a linear model. So I have showed you before that the idea is that y equals W transposed times x. This is the idea. So graphically, this means that, let's say in 1 dimension here, I have points. So this is, let's put t to say it's the real value. This is x. Well, a linear model will make something that looks like a line inside of this, of course. And you want to find the best solution. You want to find a solution such that the distance between this line and the points are minimal. So for instance, if your line is, let's say, here, it's not a good line because you see all the distances are here too much. And so what happens is that initially we have random weights. So initially you have a total random line. And then you say, okay, I have this error. I compute my gradient. I adapt my weight such that the gradient, I adapt my weight such that I follow the negative of the gradient. So I tend to be closer to this. I repeat. And so each time your line will go through the optimal green line. So it's really a learning process where you go to something that is random to something that is optimal. But here it's always a line. It's always the linear model from start to end. But you see that the idea of this learning is general. You don't have to have a straight line. Afterwards, we will see more complex models, and they also tend to optimize as best as possible the points. And you always have this idea that you have this weights that you have to choose to tune in function of the data that you see. So you have these points, you know these points. By knowing these points, you can change the slope, you can change the intercept such that it's best. So keep in mind, linear model is something that is linear with respect to the weights. And you have here a simple dot product between each point and the weights. And so it's a line graphically. If you go in 2 dimensions, it's a hyperplane, etc. And so it's, but it's still linear. So Alma Ayele, does this answer your question? Don't hesitate, because I think the difficulty for me is a bit to know what is your level, both in machine learning, in mathematics, and in algebra. So it's a bit a combination of many things, also in coding. So it will be, for some people, I guess it will be very easy to understand. For some, it will be difficult. And so we tend to make it understandable for everyone. Okay, thank you. Good.
Very clear.
So what software are you using? So this software here it's called GoodNotes. So if you want to install this software.
What is called?
GoodNotes, like this. You see? It's for iPads, you can draw and share. Okay. So, and this will be maybe important for the homework, is that remember this gradient, because you will have to implement it in the code. So it's basically the error times your data point x here transposed to make a good multiplication. And if you look at here, you see, for example, feature J, J. So it's the error. So let's say, to make it very concrete, so it's all transposed. So let's say I want to know what's my gradient. So let me give you an example, because it will be maybe helpful for the little homework. I have a simple model that wants to predict, and this will be, I think, the homework, the blood sugar level. So it's some target. Let's say the blood sugar in function of the age. So it's some parameter alpha times, or I will use the same notation, sorry. So W1 times the age plus, let's make it very simple, just some bias W0. So the bias is a constant term to the linear regression. and I want to update this weight. So I want to compute the gradient. And so here, the derivative of the loss we used before. So this is the MSL loss. If you look here, it should be 2 over the points I have times. So by simplicity, this parenthesis, I will just say it's the error I have, because this is technically just the error vector, which is a matrix, no, sorry, a vector that has the error I have on my first sample, on my second sample, on my third sample. So I have different points. Dot the feature 1. So this would be x1 for each of my samples. So let me put, and this is a bit the difficulty that you need to have concise notations, but this is the first example, the second example, the third example. Maybe I will use the same here, 1, 2, 3, so I can remove this to be concise. So in essence, the gradient with respect to the first weight are the errors across the samples times the first feature across the samples, okay? And this is how I have one value. So for instance, you have 0.25, and then you do, okay, my new weight, and you can have a variable inside Python. My new weight is my old weight minus this thing. So let's say it's 0.25. I compute it with Python, that's 0.25 times alpha. And so you just update this variable inside Python. And so with making a loop over the points and always doing this with this, you will see it will converge to something that is the same. And this is will be the solution of the weights for the linear model. It could be a bit technical for some of you, but I hope it will be okay.
A second, please. Just a second, please. So how do you decide it's 2 points? It's just you assumed, or
here?
Yes. How did you you get 2 points, or
2 points? Here.
Yes.
This is a mistake.
But it's from the equation. It's just from the equation. I'm sorry. 2 is from just the equation, or you assume that we have 2?
No, it should be 1 divided. It should be just. No, okay, of course, it's because I have, the 2 comes from the derivative, because you have a square here, it's a 2.
Yeah.
I mean, it's not important, these factors, because it's just, let's say, linear rescaling of the error that will then be rescaled by the learning rate. So basically, it's not a big problem if you put something else, but the 2 comes from the square.
From the derivation.
Yeah, from the derivation. So basically, you have, this is the error, you derive. So first you rewrite this as this times the transposed. You'd have the 2, and then you derive with respect to W. And so because it's just a product, the derivative is x, and so you put x here.
Yes. Okay. Thank you.
I mean, I think yeah.
So is that 90.25? Oh, it's a 0.25.
I mean, it was just an example, this thing at the end, the gradient with respect to, the MSE with respect to W1 is just a number. It's just, it's to show you that it's a scalar that you will have.
Okay.
So I can put here, if you prefer, the variable, this. Okay.
And alpha, we just defined it, like 5 or 6 or 10 steps, right?
The number of steps?
Alpha, we just defined it. We choose it. We assume
Yeah,
it.
that's a good point. So the alpha, typically, to give you a number, you will start with, like, say, 0.1 or a tenth or even, but this is something you cannot really know by beforehand, except the fact that, of course, you see that this update is proportional to the error itself, because when you derive the error with respect to the weight, if you have a big error, that tends to be bigger, and so it will also scale with the magnitude of the data you give. But technically, what you should do is try some values, I would suggest, and at least in the first notebook, try to play. I mean, it will be quite fast. Try to play with some values. Put 0.1, put 0.01, put all the values and see how it behaves. Does it converge? Does it not converge? How fast does it converge? And you will quickly see that this is something you have to tune. Okay. Maybe I will stop here for today because I think this is like a bit the basics. Just let me see what I have planned. This is a nice introduction.
So does the alpha has a range of value it can take?
Sorry?
Does the alpha has a range of values it can take?
The model?
Alpha.
Let me get back. So the learning rate alpha. Technically, you could take any range, but now you have to be careful that, I mean, it's like I explained before, and you have, oh, it doesn't work. I mean, if you live in a beautiful world, then this curve is convex and you can have a good minimum. But you see, if alpha is too small, you do like baby steps and you will take time to convert. If it's too big, you go from one to the other, and then at one point you are stuck around this because you go again up, again below, again here, etc. So it should not be too big and not too small. But of course, what is too big and too small depends on how your data is scaled. And this is only something you can see when you start the problem, the learning. But one thing I can say is that one thing that helps a lot is to scale the data. So if you scale the X and the Y, the Y is even not needed, but if you scale the features, let's say X, so here I have, okay, let's put the age. So let's say that the age is between 0 and 99. Well, it could be helpful to scale it between 0 and 1. And do this for every feature, you scale it between 0 and 1. Why? Because then you have the same range for each feature, and the features are not, there's like not one feature that's much bigger than the other one. Because if this happens, you need to have a different learning rate, a different alpha for each feature, which is not what you want. There are more advanced algorithms like the ADAM, and we will see that the ADAM optimizer, which is adaptive with respect to the different features. But here we have one alpha for all the derivatives. So we want to be sure that everything has the same scaling. And so you're sure to advance at the same rate on all the features. And also because between 0 and 1, you can have like values that are like this, that are quite good with respect to the weights. So scaling is something that helps. Okay. Other questions? Well, the class was for Thursday before. I think it has changed now. So what days of the week are we having for machine learning and the time? Okay. So what I have planned is, let me check. I can
Yeah,
write.
I think I sent you a schedule about this. Not you, Pierre-Paul. I sent you a schedule about it. So it's supposed to be Monday, Thursday, Friday, and then next week. So it's 25, 28, 29, and then
Yeah,
next week is Monday. I can check the email.
Yeah, I have it
I'll
here. So
forward it to everybody.
it's Monday, Thursday, Friday this week, and Tuesday, Wednesday, Friday next week. Always the same time. It's always 11 to 12:30.
Wow, wow. Oh, no longer 2 o'clock.
Is it too soon for you guys, or what?
It's better. Two is better for us, please.
I think there was an overlap at one point with another lecture. No, at 2.
Yeah, because next week you have on Wednesday and Friday next week. Then there's unsupervised machine learning with Alessandro Laio, and that's exactly 2 to 4.
I mean, I'm fine to change the other days if it's better for everyone to have it at 2. I can change at 2. For instance, this Thursday I can have it at 2. I think this is fine. I don't know if this is okay or not to change, or what do you think? From my side, it's possible to change, but I don't know if you agree with this or.
Okay, I'll send an email. Different people have different opinions.
Yeah, I mean, it's both fine, but if people cannot be here at 11, it's of course okay. You decide.
Okay, yeah, I'll decide and I'll send an email again to everybody.
Okay, cool.
Yeah. Okay, I need to decide today because then.
Yeah, so maybe I don't know how it will work, but so I think this will be the end. So this will be the end of the lecture. So there will be a notebook that I will be correcting. I will be correcting it Thursday, but I guess that we will send it by email this afternoon or something. The notebook.
Yeah,
Okay.
I can send it to everybody this afternoon. And then the homework, I'll let them know how to submit the homework so that you have a copy for each person.
I mean, yeah, we'll see. Okay.
Yeah.
Thank
you very much. Pierre-Paul.
Yes, my pleasure. I will just stop share. I want to see you back, everyone. Okay, I see you.
I have been
Okay.
asking for.
Yeah.
Yeah.